Hello, folks. Today we're going to start the next chapter of our short little mini series on videos. We're going to start about naming. This video specifically will start the introduction to naming and about the covalent compounds. Let's go ahead and get started. So, Chapter 4, Nomenclature. What's in a name? The famous Shakespeare quote, "That which we call a rose by any other name would smell as sweet." Why do we need to know about naming? Well, as we go about through chemistry, we will be constantly using the nomenclature. Being able to understand the names puts us on the same level as everyone else, being able to talk about the same things, being able to describe something. That's very important when we're talking about chemistry. We need to be able to know what someone else is talking about just by a name. If we are trying to describe, that thingy with the phosphorus and the oxygen and the so many of these and so many of those, it can be very long-winded. We need a short, concise way to all know we're talking about the same thing. Especially, while we won't cover this in these videos, organic chemistry. Molecules get to be dozens, if not hundreds, of carbons and hydrogens together, and they can all be arranged in multiple different ways. You need ways of describing this concisely so that everyone knows what you're dealing with. And that is what we need to do. Just the same way as if you're in a doctor's office, you're describing a drug, you need a way to name it. You either have the normal name or you have the actual drug name. Are you ordering Advil, or are you ordering acetaminophen, or is it something else entirely? Knowing what it's called and what the compound is called helps us all know we're talking about the same thing. So, the main focus of this chapter is chemical nomenclature, which is just simply, nomenclature is the systematic approach to naming the chemicals, the compounds. We should be able to turn a chemical formula into a name and a name into a chemical formula. And so remember, a chemical formula is made up of atoms in a given formula unit. The chemical formula is made up of the symbols of each element, with their quantities being represented by subscripts. Now, sometimes one formula unit might contain more than one group of atoms, such as an OH, and in these cases we use parentheses placed around the group to represent multiple sets of this group. So magnesium hydroxide is made up of the formula unit is one magnesium atom for two hydroxide units. Not just two oxygens and two hydrogens, but two OHs bound together. The O and the H are connected. And so if we need to represent multiple OHs, we use the parentheses. As opposed to no parentheses means each atom is separate. Now, we'll talk about the different types of compounds. Not all of them will be discussed in this video because I'm going to split this apart. But the formula units represent the ratio of the atoms in a compound, but compounds can come in various forms. These compounds could be made up of a mixture of metals and or non-metals, and two or more metals can be mixed together using a dissociated sea of electrons. This is how we form alloys. That's not going to be our discussion here. Alloys are done when we talk about solids and chemistry too. But the fact of the matter is, two metals together essentially makes an alloy. That's a completely different beast of compound. Now, what we'll talk about is two different classes, which are made up of metals and nonmetals, or just all nonmetals. When we have two or more nonmetals binding together, they bind through a sharing of electrons, which we call a covalent bond. The electrons get shared between these two atoms and thus establish a defined structure, basically a compact structure that with a defined beginning and an end. We call this a molecule. Now, this class of compounds are often called either molecular compounds or covalent compounds after the bonds they make. But the idea here is when we have more than one nonmetal, usually these guys have a defined structure that starts and stops. Now, if we mix a metal with a nonmetal, it comes together in a cation-anion pair. So the positive charge and the negative charge pair up. But because of how this works, they don't just have one plus and one minus. They pair up in a repeating style of 3D lattice structure. So it's an interweaving of these molecules together, of plus minus, plus minus, plus minus, going left and right and up and down and front and back, such that it looks like a very unique puzzle, but it's a repeating structure. It's a very repeating pattern. But it doesn't really have a set beginning and a set end. So we can't define it as a single molecule. These guys will be abbreviated by the simplest formula unit. So we won't say 50 sodiums and 50 chlorides. We will simplify it to a 1-to-1 ratio of sodium and chloride, and this will be called an ionic compound, made after the ionic bonds of the cation-anion pairs. But all ionic compounds will work in the same way. Now, before we get into any of those major ones, we need to talk about diatomic elements. Now, certain nonmetals tend to form molecules in their pure elemental state in order to stabilize their electron count. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine all form diatomic molecules. Hydrogen is that first element all the way on the left. And then starting from nitrogen on row 2 and working my way across, nitrogen, oxygen, fluorine. All those are diatomic. Once we hit fluorine, working our way down from there, chlorine, bromine, iodine. All these are diatomic. So anytime we mention any of these 7 elements, it is always assumed it's diatomic. The only way you know it's not diatomic is if we give it as a cation or anion, or we give it some special designation. So if I'm talking about oxygen, we're going to assume it's O2. If I'm talking about charged oxygen, we would say oxide, as we'll see. If we're talking about a single molecular oxygen floating in space, we talk about monoatomic oxygen. And if we're talking about O3, we have ozone. It's not called oxygen. So there's various ways to refer to the unusual forms of oxygen. Now, there's other elements that will do similar things, like phosphorus and sulfur, that form different structures, and we'll talk more about those guys later. And it's even possible that some elements are found in more than one molecular form, called an allotrope. These allotropes include, the biggest one is carbon. Carbon exists either as graphite, which is in one allotrope where we have a series of double bonded flat structures. Diamond, which is a bunch of single bonded, like, pokey structures, or Buckminster fullerene, which is a special molecular ball made up of 60 carbons, all bonded together. And that guy is essentially looks like a giant soccer ball. So these are 3 different forms of carbon, all that are essentially carbon and only carbon, but have completely different properties and structures. In the case of carbon, we'll just treat it as carbon unless we specify carbon graphite, carbon diamond, or carbon Buckminster fullerene. But here's the basics of naming. This is always true regardless of whether it's ionic or covalent. In any type of neutral compound that's made up of only 2 different types of elements, we will use this rule. And this doesn't matter whether it's ionic or covalent, this is always going to use this rule. We are going to treat the first element in our structure as if it was a cation. Even if it's not truly positive, we are going to treat it like it's a cation. And the second element will be treated like an anion. We're going to attribute positive and negative aspects to each element. That's going to be how we order these elements. It's always cation first, followed by the anion. In these names, the cation will always get its full elemental name. Now, this may have other additions onto that depending on certain factors, but the name will always contain its original suffix ending. Now, an anion will always lose the ending suffix phrase and gain a new one for IDE. In these cases, IDE tells us it is negatively charged. Now, where the suffix gets put on depends on the element. And some of them, there's similar patterns of loss, but we kind of have to recognize them with practice. So oxygen becomes oxide. Chlorine, fluorine, bromine, iodine become chloride, fluoride, bromide, iodide. Sulfur becomes sulfide. Phosphorus becomes phosphide instead of phosphoride. It's phosphide. Nitrogen becomes nitride. So it's a little bit different. Boron becomes boride. Carbon becomes carbide. It kind of jumps around a bit depending on what element. Selenium becomes selenide. It's just something we pick up with practice. All sulfur is going to be always sulfide, like that. Now, we're almost done with this first video. Covalent compounds. The big thing here is covalent compounds. How do we name covalent compounds? We're going to focus on binary compounds specifically. We're not going to do organics, just binary compounds. Binary means made from 2 non-metal elements. There could be more than one of those of each non-metal, but there's only 2 unique non-metal elements, thus the binary. When we name these guys, one guy will be named like a cation, one will be named like an anion. The second element will be named like the anion and given the suffix IDE. Now the trick here is because nonmetals are not typically positively charged, we can get a lot of unusual combinations. And because we can get a lot of unusual combinations, we need to somehow specify what this combination is, and quickly. So in this case, in covalent binary compounds, we are going to designate the subscript verbally. We are going to give prefixes for verbal prefixes for the subscript. This is not going to be the case in ionic compounds, because ionic compounds only have set combinations. There's only usually one or two ways they can combine. And so we don't need a lot of variety here. And so they follow a very regular pattern. But when covalent compounds, it can be very tricky. And so we have to find ways to name these. Now, we're going to give a prefix for both the cation and the anion. However, if the first element, the cation, is 1, we're going to assume it's 1 and leave that prefix off. So we're always going to assume the first guy is 1 unless otherwise specified. But the second element must always contain a prefix in these binary compounds. Now you see on the right, up to the first 10 of numbering is given. So mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Pretty straightforward. It's the prefix. Mono means 1. Like monotone voice. Without any ups and downs, no hills and valleys, it's monotone. Di, you'll learn about in biology, dimers, trimers, and tetramers. 1, 2, and 2, 3, and 4. Monomers, these polymers. If you look at, like, say, hemoglobin, for example, that's a tetrameric protein. It has 4 individual sections with hemoglobin, with iron porphyrins capable of bonding oxygen. Penta like pentagon, hexa like hexagon, octa like octagon, deca like decagon or decade, 10. So all those are pretty straightforward. If I have NO3, that is nitrogen trioxide. So the first guy is named like a cation, no change. Because it's 1, we just call it nitrogen. Oxygen is converted to oxide, and because there's 3 of them, we call it trioxide. Now the next example, dinitrogen pentoxide. Well, it's still nitrogen, but now there's 2 of them. And because it's no longer 1, we have to specify it's 2. Oxygen still becomes oxide, but because there's 5 of them, we call it pentoxide. Now the one major exception is any compound that contains hydrogen. Most hydrogen compounds will become acids because of how hydrogen acts. So they will be named differently. And even if it's not a true acid, they still get often an unusual name, so we will not name them like this. There will not be dinitrogen, let's say dihydrogen sulfide. No, that's not how we're going to, monosulfide. That's not going to be how we name it. Like NH3 is ammonia. You may have heard it as a cleaning solution. PH3 is phosphine. It's a poisonous gas that can be produced when you're making meth. So, okay, we're going to this practice. This will be our last slide. I know it's, whether you think, oh, we spent way too much time on here, we spent just enough time on here. This is awesome. So, recognizing the elements is the key. This is P, it's phos for us. It's the first element, so it gets the name. Br is bromine, so bromide. Bromide. And because there's 3 and 1, we're going to leave the mono off, and this is phosphorus tribromide. Seen this before. C is carbon. O is oxygen, so it becomes oxide. And there's 2, so we call it carbon dioxide, the basic gas we exhale when we breathe. Now, we usually just call this water, but if we were to name this binary, we have hydrogen and oxygen becomes oxide. Now, because this is 1, it's monoxide. And because this is 2, we'd call it this dihydrogen monoxide. So, keep working. SO3. So we have sulfur, oxygen, oxide, and there's 3 of them, so we call this sulfur trioxide. This is arsenic, then oxide. There's 5 of this, so it's pent. And there's 2 of this, di, so diarsenic pentoxide. See how I'm breaking down? First guy, just the element. Second guy, element plus ending. Second guy, prefix. First guy. So, this is tellurium, not a usual one, tellurium. And then we have chlorine, so this becomes chloride. There's 6, so it'd be hexachloride. SB is an unusual one. You might have to access the periodic table, but SB is antimony. Antimony, that is nitrogen, so it's nitride. And because there's 1, it's mononitride. We have nitrogen, and that's selenium, so it's selenide. There's triselenide, dinitrogen, so dinitrogen triselenide. Lastly, carbon, that's oxide. This is carbon monoxide, that dangerous, deadly gas that is exhaled every time. Well, it's produced by the incomplete combustion of many fuel sources, such as charcoal. One of those reasons why we suggest you don't cook in an enclosed room by charcoal, because of the buildup of dangerous carbon monoxide gas. Now, while I don't include this in this video, normally on these slides, I will do a quick example of going in reverse. If I said dinitrogen monoxide, what would that be? Dinitrogen monoxide. So we have nitrogen, that's an M. Oxide, that's oxygen. Di means 2, mono means 1. N2O is dinitrogen monoxide. This is laughing gas. You ever breathe that in the doctor's office? This is what you're inhaling. If I had, let's think of one more. How about carbon tetrachloride? Well, we have carbon, we have chlorine, and tetra means 4, so carbon tetrachloride is CCl4. Maybe one more real quick, and that is And that would be, let's see. Oh, I did that one. So let's see. Oh, I'm trying to think of some of. Here we do oxygen monofluoride. So that'd be O, that'd be F. So OF. O of 1. So this guy would actually be some very powerful, very reactive gas, but just know that it's O1F1. That would be how you would turn the name back into the structure. But that's where we'll be stopping for this video.